Mall. John Mall received his education through Florida State University. Over the years, John has gained invaluable environmental experience while working in the mining and landfill industry across the country. John, in conjunction with Clark Hughes, are the inventors and owners of the Crystal Stream Technologies. John currently operates as CEO and oversees and directs all research and development and engineering services for Crystal Stream Technologies. He's also a key member and founding member, as you guys have heard in the past, I believe, of Stormwater Equipment Manufacturers Association, or SWEMA for short. At this time, I'd like to welcome everybody, and I'm going to turn the floor over to John. Please join me in welcoming John, and John, it's all yours.
You're getting pretty quick at that, Jeff. That's pretty good. I appreciate that. If you guys noticed, I typed the address of the Stormwater Association down there. A couple little things I'd like to remind you of about the Stormwater Association. The Stormwater Association is directly involved in setting standards and sizing and in the approval of these manufactured technologies. This has been a long time coming to our industry, and it's a good thing. And right now we're working through up in the state of Tennessee with the Tennessee Stormwater Committee, but we're also working with NJDEP and a review of what that system, the TARP system, has been. So you'll hear some good things, and it's good to keep checking back at that
John,
Stormwater Association site. Yes?
Hey, John.
Yes, Jeff?
It seems like you might be getting a little bit of an intermittent signal or a breakup. Is anybody else experiencing that? If you could just type an answer down in the lower corner there. Earl or Charles or anybody? Okay.
Yeah, my signal's showing pretty good here. We'll have to get you a better connection up there, Jeff. Okay. Thanks, Jeff.
Yeah.
You might want to check back with the Stormwater Association, because as these things go forward, there's going to be a lot of work done in helping both specifying engineers and jurisdictional authorities in helping set what these standards should be, and you're going to see some good leadership come out of this effort. What I want to talk about today is a subject that we broached in our first meeting of the Stormwater of SWEMA, and it's very interesting because people have seen low impact development as the wave of the future, and it is. For a lot of reasons, and at the same time they've seen kind of on the other side manufactured devices, a BMP in a can, if you will, or a magic box, as some regulators like to refer to us. But this subject today on water quality and water quantity shows how we can perhaps marry those two together and come up with some better designs that'll help. Probably, I know John Livingood and Charles Cook, Earl Duckett, Mark Romano. I'm dealing almost exclusively here with PEs and guys that know hydrology inside and out. But you may share this presentation with some other folks, and not everyone is real versed and well versed in how water quantity control happens. Obviously, to avoid overloading downstream pipes and swales and discharging excessive flows, over the years we've come to use detention ponds with outlet control devices, which has almost exclusively been the method of choice for controlling the quantity of water coming off of sites. It's well-known technology. It's something that engineers are comfortable with. The idea is that if I live downstream from you, you're not going to produce a higher flow coming off of your site than before the development of your site. Everyone understands that more water runs off of impervious surfaces, so developed sites generate higher rate of flow. And not everyone takes the time to think about the fact that there's also more quantity of flow coming off. So when water flows into a pond at higher than the allowable flow, the flow out has to be controlled, usually through a weir. It's placed at the exit to limit the outflow. Obviously, since water is flowing in faster than it flows out, you have to detain some of the water or store it in a pond to achieve the detaining the detention of water on a site so that the flows off site can be maintained. Well, most engineers and hydrologists agree that about 95% of the water that falls on impervious surfaces will run off. Now, this absolutely is not true in a small, light rainfall in the summertime that's falling on hot asphalt. But overall, over the course of the year, engineers like to use a 0.95, which is 95%, or a 0.9 runoff factor for impervious surfaces. On landscaped areas that are developed, it's possible to get less than 50% runoff. Lots of engineers like to use 30 or 35%. But by the time you compact soils and there's a relatively thin layer of manufactured soil underneath them, usually it's good to assume about 50% runs off. Now, in an undisturbed forest land, only about 20% of the water runs off. Sometimes it can be a lot less, depending on the type of land. And that runoff usually only occurs after the ground is saturated, because the leaf canopy and the organics on the floor can absorb some of that water. Now, these are just general numbers, but they're useful for our discussion here to talk about why we need to control water quantity. So if an inch of rain falls in a forest, let's just say about 2/10 of an inch runs off. When you make that forest land pavement or rooftop, almost all of it runs off, which is about 5 times as much quantity, not rate of flow, quantity. Even in landscaped areas, it's 2 to 2.5 times the runoff as it was when the land was forested, let's say. Now, the other factor is that water moves more quickly in general across a paved surfaces or in a pipe. So not only do you get more water running off, you get faster. The water runs off faster and peaks sooner. This is, for those of you who aren't familiar with weirs, this is a picture of a V-notch weir. It's just it's in a concrete environment where there's some ponding behind it. But there's different structures that can control the rate of flow out of ponds. This particular weir gets wider as it gets deeper, and so obviously it can allow more water. As the depth of water increases behind it, it's not just a linear increase. The water increases, and you can control this by the angle of the weir, the depth of the weir. V-notch weirs are used a lot to control water. So this helps match pre-development flows. Usually a jurisdiction will say you need to match the 2-year, the 5-year, the 10-year. Some, they pick some storms that they want to see the flows matched and kind of test your system to see if in various types of rainfalls the rate of flow, not quantity, this is the rate of flow in cubic feet per second, to see if you can match that flow coming off the site. Well, a V-notch is a nice little piece, a nice little tool, because obviously lower flows mean less detention, and less detention is a lower profile here on the weir, and so this can be used to match small storms and larger storms. Now, engineers use weirs, broad-crested weirs, and sharp-crested weirs, Ogeechee weirs, circular orifices, all sorts of techniques to try to tune their release of water so that it remains the same. Now, detention ponds do have some water quality features to them. I've got a picture here of a detention pond that's just full of trash and debris, and probably some extra sediment too. There are some gross sediments and pollutants that are caught, but even though the rate of flow is similar to pre-development, that flow lasts longer and much more water reaches the stream when the pond has emptied. The release of water is over a relatively short period. It may take a couple of hours for a pond to drain down, but that any treatment that happens in the pond is relatively limited. The larger particles are caught similar to manufactured devices. But because these ponds, outlet control structures, tend to be a fairly high energy environment, sometimes there's material that's lost around the outlet control device. The footprint of the pond is small in comparison to the impervious surfaces on the site. So the infiltration into the groundwater table is limited for a pond. And the largest storms can cause the pond, as it's shown here in the bottom here, to overflow past the weir, and a lot of the captured material is lost. One of the effects we found by putting devices below pond, which is actually not where they belong, is that we still get a lot of material in our devices below the pond, and it's because when that pond does go to an overflow or it gets into a large storm, it's pretty violent. The flows and the turbulence inside the pond is pretty violent, so we see a lot of material that gets washed out. And that's not to say detention is not a good practice. In fact, it's hard to find a jurisdiction that does not require detention. There are very few exceptions to detaining the water, and it is justified to protect nearby properties. And you'll have pipe systems, downstream pipe systems that were sized for the existing flow, and so if you increase the rate of flow, you would overload the pipe system or the swales or ditches. So, but you really can't address water quantity problems with a detention pond. The quantity of water that runs off is exactly the same, pond or no pond. It just runs off more slowly. As a larger percentage of the properties developed across a watershed, these ponds peak and release at different times, and so more and more water reaches the stream. As an engineer, we've spent a lot of time justifying the fact that at the 10-year storm or at the 5-year storm, at some particular point in time, that we are not increasing the flooding on a stream at that point. But if everybody's releasing 3 to 5 times as much water into the stream in a watershed, you can bet that stream's going to receive more water overall during a storm event. While the pre-development flows were smaller, they also took longer to reach the stream. And base flows from groundwater tables maintained some flows even during periods of little rainfall. You see this a lot up in the mountains. Sometimes I've seen springs in the mountains that there's so little mountain above the spring, I wonder how that flow is maintained even during the driest months. But there's a tremendous amount of storage capacity in soils that water moves very slowly through this system. And so not only did we have less flow going to the stream, the water that would have gone to the stream quickly and after a property was developed and gone downstream is stored and reaches the stream in a measured basis over time. The post-development conditions do produce higher rates of flow and higher volumes of the flow immediately after a storm. But there's little or no base flow between storms because we're covering areas that used to be able to infiltrate water, absorb water, and we're not allowing that water to get in the ground anymore. As a result of these activities, the channel of the stream must widen to accommodate the higher flows. And so the whole morphology of the stream changes over time. If you work with some of the stream experts who are looking at channel bank erosion and are looking at the outside curves of streams, they get pretty good at being able to estimate the amount of impervious in a basin just from the change in morphology on these streams. So, the question is, how can we, when we're doing our water quality efforts, how can we help the water quantity problem? Well, even if we treat the water coming off of a site prior to detention to an extremely high level of quality, we use a separator, we use a filter, we would not help the quantity problem at all. The channel banks would still erode. The excess water going to the stream would still be there, and we would not have the groundwater recharge that we're looking for. So, although this presents large engineering problems and some complexity in the design of a system, the first goal of a water quality plan must be to limit the flows of water off of the site, because that uncontrollable extra water that gets into a stream channel is something that happens off of a site, can't be measured at the outflow point of a site, but it's a definite impact on the basin. Well, the best way that we know today to do that is through infiltration on the site or reuse on the site. And both of these techniques require some attention and they require some complexity. If infiltration is possible, and that's one of the first levels of complexity, there's a lot of areas where infiltration is very slow and some areas where it's not possible at all. But if it is possible, it will help support the water table and stream base flows. Reuse for irrigation can also support infiltration to the groundwater below landscaped areas. In other words, you could irrigate a landscaped area and have the runoff go to a infiltration based on something like a bioretention or an infiltration swale, this wouldn't be rainwater that's coming off of a parking lot full of grease and oil and trash and debris. This would be water that has been gathered into a cistern, pushed through an irrigation system, relatively clean water, that may run off, and it could be used for infiltration after it has had that piece of the treatment train. And there's reuse for gray water can save some critical potable water supplies. There's a two-edged sword. Theoretically, it's good to protect the streams and save the channel bank erosion downstream. But if you gather water either for irrigation or for flushing toilets or for other gray water uses like washdowns, this is saving you paying for water that's coming in through your meter, water that's had to be treated to drinking water standards by the jurisdiction or the municipality. And so a lot of times when we're looking at the complexity of getting a reuse system in place, we're not necessarily paying close attention to what may be saved in potable water supplies. So there's a positive effect there too. Well, there's the challenges to this, and I was speaking today, Earl Duckett's in the room here. I was speaking today with Earl Duckett, and it's always good to have these holistic, overreaching ideas about, gosh, let's let less water flow off the site. Well, what are the challenges about on-site reuse or infiltration? Well, stormwater is dirty. We know that because we maintain almost 500 devices, and we've done over 5,000 clean-out operations, and we see, I had a report yesterday in the winter time from Highlands, North Carolina, very cold up there, of a live snake and a live bullfrog inside our device at Highlands. And it was interesting to me that they understood pretty well that it was cold outside and that the soil is still at 18 degrees Celsius or so up there, 60-ish, 65-ish inside our device, and they had found a warm spot literally to take up residence. But stormwater is dirty, and by the way, our cleaner told the city folks that were up there to observe the cleaning that, hey, this just shows how good we clean up stormwater, and I thought it was kind of nice. Second thing is the challenge is rainfall is chaotic. You just don't know. We have average yearly rainfall in Atlanta, 85 events a year, somewhere around 50 inches of rain if you look at the last 30 years, somewhere around 54. If you look at the last 50 years, you can do some predicting when you get to 30-year periods or 50-year periods. But really predicting, even in a storm you know is coming, the intensities and the depth of rainfall can vary widely just a few blocks apart. I've got a picture here showing rainfall where it's just getting slammed over here, and these guys are nice and high and dry. So it's very hard to predict what the inflow rate into your cistern or into your infiltration system, or what the force and power that washes off of your site is going to be in advance, and to design a system that will take care of that. And the third challenge is owners. Site owners are uninformed. We talk about this in our circles. We talk about this as designers and engineers and jurisdictions and the folks that are writing the permits and the EPA and rules and regulations. And when the rubber meets the road, most owners that have a BMP don't know it's a BMP. If they do know it's a BMP, they almost certainly don't have a manual or a checklist or anything to keep it working properly. And the ones that do know all of that aren't real happy about spending money for the kind of misty, unclear goal of taking care of the watershed. So these challenges exist. If we're going to do something that's more complex than putting water in a pipe, putting it in a pond, that we hopefully, in the old days, we would design it so it wouldn't silt out, in a pond that's going to be 10 years for maintenance or 5 years or 20 years. We just push the problem downstream. If we're going to do something more complex than that, we've got to go after these challenges. Infiltration and reuse systems. Every one of them has a very similar need. This includes manufactured filters. It includes cisterns. It includes distribution systems for landscape irrigation or for into a toilet system, let's say, for flushing in a building. All the water that comes to these reuse systems should be free of excessive sediments and gross pollutants. You just can't deal with Dixie cups in a lawn sprinkler system. So step one is to be sure that the gross pollutants and sediments have been removed from this water, and this is something that's been shown to be very easy to control. There are a lot of systems out there, mostly manufactured, but there are good sediment forebays and trash screens that have been able to control this type of material getting downstream. A manufactured device, for example, may look something like this bottom picture down here, nothing more than a manhole or two on the site. So the impact for land use is very, very small. And this could be true of a public domain vault in the ground that was settling out sediments. It doesn't have to be a manufactured system, a proprietary manufactured system. But one of the things I keep in mind is that every pond out there has been manufactured. It certainly wasn't a natural occurrence. I have seen a very few natural lakes and wetlands used for stormwater treatment, but when I say very few, I can count them on one hand. So whether it's a manufactured system or a public domain system, the material captured should be able to be easily removed and disposed of. One of the knocks on manufactured products and one of the knocks on good filtration products, both manufactured and sand filters and things like that, is the material captured is hard to remove and hard to dispose of. I will tell you this, that in general, the land-based systems are much more difficult to maintain than the manufactured system because we do both. Now, when you build a manufactured system and you try to get it approved, the first word out of a regulator's mouth, and it should be, is, hey, how are you going to get that thing clean? What does it cost? How often do you have to clean it? What's going to happen if it doesn't get clean? Those questions should be asked for every B&P, but when we talk about dirty water and getting it clean so it can be reused, these are the types of systems that you need up front to pre-treat this stuff. The problem of chaotic rainfall is certainly not one we're going to solve, but one of the problems with infiltration is that it's very slow. We can design sand filters that will infiltrate relatively fast compared to soil, regular soil. But no matter what the system is, compared to a 36-inch pipe going through a pond, it's awful slow. And that's something we have to deal with when we're looking for solutions. Bioretention has limited storage before it overflows. Reuse systems have to hold enough water to provide for irrigation or other uses. One of the problems with irrigation cisterns is when it's raining, which is when you get your water, you don't need your water because it's raining. So you have to store that water. You may have to dispose of some water when you have a large storm coming and your cistern's already full. So all of these problems of the chaotic nature of rainfall have to be addressed when you're dealing with this type of a system. Large storms can be a problem for infiltration or bioretention. So you want to have overflow from these systems that can be redirected to a reuse facility or detention. Now, reuse can be a problem because of invert. We always talk about water. Everybody understands water goes downhill. Detention, it's pretty easy to get this water to a detention system, which is usually the low point on the site. Very few stormwater systems pump water up to detention. So planning in advance for overflow from infiltration or bioretention, what are you going to do with the water if it overflows? This starts to let us know that when we're going to do these type of controls, infiltration or bioretention, it would be really nice to get them up higher on the site, which means closer to the source. So maybe 2 or 3 smaller bioretentions as opposed to one big one down at the bottom below a pond or something like this. Small storms may not provide enough volume for reuse, while large storms can overflow a cistern. Cisterns, and this is a relatively new technique, can be used to irrigate an infiltration field, something like porous paving. We've suggested at a major grocery chain who wants to meet the lead requirement of never discharging the water quality storm, not a drop, that if we have a full cistern and a storm is coming, that they could use pavers or porous paving on the up side of their least used parking, the highest point. And instead of having water flow down into porous paving where it could block or clog the pavement over time from oil, grease, etc., we would simply spray clean water on it and place the parking where it was the most inconvenient for people to shop. And perhaps by doing that, we'd have a way to dispose of the water into an infiltration field if we needed to empty that cistern ahead of a large storm. And finally, irrigation can also be directed to runoff I put irrigation here, but I should have put infiltration or bioretention areas. So when you do spray with your lawn sprayer, with your lawn sprinklers, instead of having that water run directly off of the site or to the detention pond, it's not going to have a lot of big trash in it, and it may have some chemicals from your lawn in it, but it would just be the perfect thing to direct to irrigation, infiltration, or bioretention system. How much is enough? In most areas, if we talk about a 1-inch first flush rainfall depth, it'll account for about 80 to 90% of the rain that falls every year. Now, if you go do the math, and being a curious person, I did that. I took all the storms for the last 60 years in Atlanta, 1 inch and below, and I added them up to see the total rainfall depth over that period of time and the depth of those storms, and it was only about 65% of the storms amount to this 1 inch or smaller storms. And being a flow-based device, it bothered me that we weren't quite getting 80 to 90% of the rainfall that falls. What I missed in that was every storm that's larger than 1 inch, if you're a volume-based pond, well, you're going to get the first inch of that storm. So it's an 1.5 inch storm, you get the first inch. When you add those storms into the mix, and by the way, you can add them into the mix for the rising limb of a hydrograph, 1.5 inch storm, a flow-based device is going to treat a good portion of that as the flow builds. So that's how you come up to the 80 or 90%. If any of you guys are trying to do the math, which is casual, so to speak, for if you're trying to meet a permit, but when you're trying to fill a cistern and estimate the amount of water you need to maintain landscape, it's no longer casual. You need to have a real good handle on the distribution of the rainfall and what you're going to get and what months of the year you're going to get it and when you're going to need to irrigate. So keep that in mind as you're starting to sum up these storms. Well, if forested land only has about 20% runoff, that means if you catch the 1 inch storm, you could match the existing volume of runoff. What I'm saying here is, let's say we catch the 1 inch first flush, and in Charlotte, North Carolina, it's 80% of the rainfall that year. Well, that means 20% of the rainfall would run off, which is about what we had when we had forest on the land before. Now, the flow patterns would be different. The times that it peaked would be different. There'd be a lot of storms where there would be no runoff. There'd be some storms that would provide more base flow and more infiltration, and there'd be some storms that provided none at all. But getting close to the pre-development conditions for water quantity would kind of be a serendipity. It'd be kind of a nice piece of fallout from the fact that we were trying to do our water quality. Remembering that whatever water we keep on the site has 0% concentration of pollutants. So if you could catch 80% of the water, you could make an argument that you were catching 80% of the pollutants because that 80% of the water didn't run off at all, so there's nothing being carried off the site. That's a whole different argument, but it is something that could give you some comfort that most of the water is not running off the site. But realistically, you're not always going to have a site, and certainly not one that can infiltrate that much water, and maybe not one that could reuse that much water. If you look at the ratio of the landscape on, let's say, a burger operation, a hamburger operation, you've got a lot of roof, you've got a lot of paving, you don't have too much landscape. There's not a lot of places to put that water. If you don't have some infiltrating soils, you're going to come somewhere short of meeting your volumetric goal. But anything you can catch and retain on site will help meet that volume goal. When you're thinking about the cost of building a pond, the size of building a pond, the depth of the pond, the cost of the outlet control structure, the size of your pipes, there are savings that cascade back upstream over the fact that you've handled some of your volume. In fact, you may find that you meet your 1, 5, and 10-year storm requirements, release requirements, because you're capturing a certain amount of that water and keeping it on site. Well, there's some simple steps that can be effective to help you do this sort of thing. On tough, and that's what I was talking about, on a tough commercial site, the rooftop sometimes 30 or 50% of the impervious surface on site. This water is essentially clean and doesn't need pretreatment. Now, I know if you've got a dentist office with oak trees over the whole roof, you've got leaves and gutter, but thinking more of your more typical commercial sites, this water is essentially clean. It doesn't need pretreatment, so you're not going to spend a lot of money with a manufactured device or a filtration device or something to clean that water up. You can use that to fill a cistern for irrigation, or for wash down, or for other purposes where you would normally be buying water from the city to accomplish that task, drinking water essentially. It can save some expensive potable water for use. Here in the east, we're blessed with a lot of water. There are people out west. When I went to Utah complaining about the fact we were in a drought, we'd only had 35 inches of rain 2 years ago, they were laughing because they get 17 inches of rain, I think 7 inch of which comes in the form of snow melt, and our drought would have been their flood. And water is precious. So saving water is a way of life in some areas, and for some of us in the type 2 rainfall areas in the east and around the coast, we don't think so much about these techniques, but they're not exotic techniques. They're things that can be done fairly simply. And the irrigation at a rate that fosters infiltration and avoids runoff. If you irrigate your landscape at a high gallon per minute volume, which might let you run your sprinklers for less time, you may have water that runs off and enters your detention pond. You can slow that down, and you can also irrigate at times that would be the wrong time for irrigating if you were buying water. In other words, buying water, you might want to irrigate at night, water down, let it do the best for your plant materials. If you're trying to waste water, so to speak, and get rid of water out of a cistern, irrigating during the day, during the hot part of a day, might be a smarter thing to do, and irrigating more slowly so that the water would avoid running off might be the thing to do. And you can incorporate rain gardens or bioretention for irrigation, not parking lot runoff. What I'm saying here is some of these things that make no sense, that are connected up to a parking lot with 1,200 automobile trips a day, like a gas convenience operation. Putting a bioretention or rain garden out there, to me, is just irresponsible. It's going to be dirty. It's going to be nasty. It's going to be a mess. It's going to smell bad. It's going to be full of oil and grease, and it's just not smart. But if you had, let's say, slopes that sloped away from your parking lot and a swale at the bottom that you could have a slow release on, this might be just a perfect place to get in some rain garden or bioretention. Water quality points, save some money, and actually do some good for the environment. Owners are uninformed, and this is a monster problem. I think everybody's starting to realize it today. But our experience, and now I'm talking about my cleaning and maintenance company, most owners have no idea the function of any BMP that they have on their site. You can't find manuals. Properties where we give the owner a manual and go back in a year, there's nowhere to find the manuals, nowhere to be found. We've done our education. We've at property turnover. We've done everything we can. We're trying to push them and guide them into maintenance because we're in that business. But in general, if someone like us isn't staying at this all the time, these owners certainly don't have manuals and resources to guide them into how to properly maintain and keep up ponds and sand filters and everything. Every BMP should have a manual that shows proper care and maintenance. Maintenance procedures and costs should be disclosed at the issuance of a permit. Engineers in the group here today, I say at the time of a permit, really, you should be sitting down with your owner and say, look, here's the responsibilities going forward you're going to have for water quality. Here's what we know are the permits and regulations today, and here's what you're going to need to do, and here's the cost. We can save some money up front and do this, and it's going to cost you some money in maintenance down the line. But you really should disclose what those maintenance procedures and costs are before you put a BMP out there on the site. And I think all of us know this, and I could be really critical of engineers and designers, but I know we've been diligent every single time, and we've had a horrible success rate overall for implementing maintenance on BMPs. You know, it's not necessary. Jurisdictions can help with this. You don't have to have an army of BMP police to enforce maintenance. Similar to the programs on most detector checks that have to be inspected yearly to avoid water flowing back, contaminated water flowing back out of a sprinkler system or whatever into, or a local fire protection system into the potable water. Owners can self-verify at a proper maintenance or inspection interval if they know what to do. And you can have simple records like disposal manifests or receipts for services with some digital pictures to verify compliance. We're actually doing this in some areas now. Provide a log sheet for the owner at each maintenance interval. You know, 6 months inspection on his pond for whatever, or a 90-day inspection. When reports are late, a simple reminder from a jurisdiction may suffice to get an owner to get his work done. And if a live inspection is required, charge a fee. So this is my little picture here of trimming a pond with the inspectors coming, and I've literally seen this occur where landscapers are hired at the last minute to try to make a pond look good because someone's gotten a violation and the inspector's coming back. You really should have a checklist, something like this. This is our checklist for our device. When we don't have a device under cleaning and maintenance, we certainly can provide this to the owner. We have a 5-year warranty on our machine if it's cleaned, and this can serve as a reminder to the owner that there's some things he's supposed to be doing. This is a manifest. This is a nice piece of paperwork because the generator signs that you picked it up, and he generated it, you picked it up at his place. Transporter signs that he transported it to a disposal facility, and then the disposal facility signs that it was disposed of properly, and there's a receipt for the gallons and the money, etc. And things like this can make it easy for an owner to comply. You know, he can send a county or a city, he could send them our checklist, our manifest, and a receipt for what he paid, and he's in compliance for another year, another 6 months. It's a fact that without a good program, BMPs are going to fail, and especially what we're talking about here. If you're trying to address water quantity with some infiltration and reuse, you're not going to have a system that's going to function unless somebody understands each element and how it's supposed to be done. It doesn't have to be overcomplicated, but it's pretty simple to inspect and keep these systems functioning when you're paying attention. We try to make it easy. You know, we want to encourage owners to maintain their BMPs. We try to sell maintenance, but you know, I'd have to give us an F, our report card, because we're right at 1/3 of our devices are on active maintenance, and this is with it's to my benefit to get these guys on maintenance for several reasons. Number one, the machine is doing what it's supposed to do and what I sold it to do. Secondly, I make money, which is good. It's not a monstrously good business, but it is a solid, steady business. It's not as much fun as designing and getting patents and things, but it's certainly a piece that needs to be done. And thirdly, the jurisdiction has some confidence that what we all conceived of, the regulations we wrote, the plans we filed, are actually happening. Well, with a concerted effort in my own interest here, we still only are successful 1/3 of the time. Over time, if no communications come from the jurisdiction, owners will quit. We've got some people now that are coming back on maintenance for their 3rd time, and that means they've had 2 NOVs. And when they get a notice of violation, then the inspector comes out, they'll get back on maintenance. It's tough, but that's kind of the way life is. So we have to understand, unless there's a good program for enforcement, even if it's a friendly enforcement program. So we also call jurisdictions to get a request for BMP locations. My guy will go out and offer to clean the pond, clean the swale, clean the competitor's device. You'd be surprised how many jurisdictions have no idea where their BMPs are. They offer to give you the key to the plan room. You can go look through them and see what you can find. and certainly don't have a program for inspections. Now, to be fair to the jurisdictions, inspections during construction are scheduled, programmed, and there's a whole program of when your next inspection comes. You get this done, you call the electrical inspector, or you're going to get a soil and erosion inspection every 2 weeks, whatever. But post-construction, most all inspections in the county are driven by complaints. And so essentially, if it's in the ground, out of sight, out of mind, the pond's not overflowing, and there's not shopping carts going down the creek, you're not going to see an inspection for water quality. So here's the kind of a recap of actually accomplishing water quantity with water quality. Okay. Step one is to address runoff volume first, retain and reuse. Is that going to work on every site? No way. Maybe it only works 50% of the time. Maybe it only works 30% of the time, depending on the type of sites that you have. A scrape and rebuild downtown, kind of tough to retain and reuse. Certainly, if you've got a wall-to-wall building and a 4-foot sidewalk or a 6-foot sidewalk in front, you're not going to be doing much. But on the other hand, if you realize that this may save your owner some money in the long run, may cut down the size of your pond and get you a better yield out of your property, more parking, more building, something to consider, because the cost of that land is very high. And so look at runoff volume first, see what you might be able to do. Limit the exposure of relatively clean water to hard surfaces. Sometimes they need to put downspouts out onto pavement, not always. There's good reason to pipe water on a site to control it so we don't get erosion and high maintenance later on. In other words, we prefer pipes over swales a lot of times as engineers, because once it's in the pipe, it's good. Not such a bad idea. Lots of people pipe downspouts today to control that water around a building, control moisture in the footing. I mean, there's a lot of reasons to do that. So maybe there's a good reason to take this water that comes off of a roof and not necessarily run it across your parking lot. It might be your habit, but maybe it's not the best practice for several reasons. You got to protect source areas. The places where your dumpster sits, the places where your trucks park, there are ways to keep that water from commingling with the rest of the water on the site. We even have started making kind of a dumpster machine, a little bitty thing, that will take that water and treat it small, runs slow, but it keeps us from putting this water straight up into detention ponds and other places where smells and odors and other things can be a problem. Disconnect sites impervious where possible, of course. Pre-treat ahead of ponds infiltration and bioretention. That's kind of been a central theme today, but these are the design factors. When you sit down with that site and look at the building you got to get on there and the parking you've got on there, you can start looking for places that might work, places where you might put in a lineal swale, places you might slope your landscape to help you with this quantity guy up here. Okay, and then pollutant removal and moving water is the worst case. It's tough. The benefits: reuse saves money. It can be a good payback. There are companies today that are going out and selling to office parks and apartments the benefit of putting in a cistern to reuse and save money, and they're talking about 5 to 7 year paybacks, to where it's that reduction in potable water is going to actually pay for this system over time. I don't have all the math on that, but it's definitely true that it can save money, and of course it helps the environment. It can save land. That's probably your biggest ticket number. If you could make your pond half as big, that might be just the thing that gets you onto a site where you couldn't get on the site otherwise. Maintenance is simplified and costs are identified up front. By putting maintenance, the gross pollutants, the sediments into an easily identifiable BMP with a maintenance contract, you take care of life for your owner. All of this stuff works better. His pond lasts longer, his infiltration lasts longer, and you are actually bringing a benefit to your owner instead of a cost, just to try to meet water quality requirements. And then the removal of material provides a tangible result. I never realized how valuable this was, but both in cities and towns and companies, we've been able to give them, well, we call it the Ton Club. We put DeKalb County at one point, I think, into the 600-ton club. We had taken 1.2 million pounds out of material out of devices they had approved for us within their jurisdiction. And so we have a little plaque and a ceremony, and we go up and explain to them how good they've done. We just put Elizabethton, Tennessee into the 50-ton club this year, a smaller city with less devices. But this tangible removal material that shows how many thousands of pounds of material that was going to go to the streams and rivers is a tangible result. This actually gets jurisdictions and it gets owners fired up to try to do some water quality. So if you're remembering that removing pollutants from running water is the worst case, and it's tough, every gram of pollutants that don't enter the water makes the job easier, and you can control your sources. I'm not an expert at source control, but there are a lot of things that can be done. Roof materials, types of paving materials, other things that can help control the source of pollutants that are going to get in the water. All the water retained on the site, of course, reduces the rate of flow and the duration of flow, and that really helps in stream bank protection. And I think most of you guys have seen more and more jurisdictions are requiring retention or reduction of quantity for stream bank or channel bank protection is what most of them call it. In the removal process, if we are having to remove pollutants, slower is easier. So the less load we get and the less flow we get, the more successful we can be at using mechanics, using gravity, using flotation, using centripetal force to remove pollutants from stormwater. So you don't ignore the design factors that can make the process easier, because this is where your real savings are. You got to remember always to pre-treat ahead of ponds, infiltration, and bioretention. There is no mechanical separator like my crystal stream device. We have a polisher too, but a mechanical separator, a gravity separator, cannot remove salt out of salt water. Can't deal with dissolved chemicals. So these BMPs, ponds and infiltration, bioretention, can do things that a mechanical separator cannot. But it's almost like there's a divide down the middle. The ones that can handle the dissolved chemicals and the nutrients cannot handle trash and debris and oil and sediments. So these ponds are very difficult to maintain. Infiltration, this is an infiltration system. Sand filter is just practically destroyed, not working. They will fail without some protection. So that's something to keep in mind if you're going to do this. Well, if you aggressively design for water quantity from the beginning on your site, you may find that your water quality needs have just about gone away, that you have accomplished water quality simply by addressing the quantity issues up front. No runoff for a subset of storms means there's no pollution leaving the property for those storms. One of the odd things that happened as LID was being evaluated in the early days, in the late 90s and early 2000s up by the Center for Watershed Protection, is the effluent quality went down. In other words, the water got worse on the subdivisions that were practicing LID. There was higher concentrations, and the reason was there was less runoff. Overall, there was a lot less pollutants. In other words, if 1 pound ran off before in 10,000 cubic feet of water, that was a low concentration. Later, a half a pound ran off in 1,000 cubic feet of water, so the concentration went up, but the total net volume of pollutants going off the property went down. So every time you can cut the pollution down to zero for a storm, it obviously goes toward your favor in the percentage of reduction. Some people have asked me, how do you get 65% removal of phosphorus? Well, only flow 30% or 40% of the water off your property. You can show some level of reduction there, but 60% of your phosphorus never got a chance to leave the property. And mechanically, it's hard to get 65%. By absorption, it's hard to get 65%, but you can make a solid case by reducing the volume of water and not allowing it to leave the property that you've reduced some empirical amount of pollutants that come. A detention does not address water quantity at all, but you can reduce the size of your detention pond, obviously, by volumetric treatment, by quantity treatment. Stream base flow and groundwater needs to be addressed, it would be hard to make the stretch to say, gosh, we're going to cure all the groundwater base flow problems by infiltrating, because the fact of the matter is, first of all, infiltration is hard to do. It's not that fast. Once you get away from a natural soil, you've really hurt the ability, and it's hard to clear a property. It's hard to certainly can't compact the soil on a property and still get infiltration. It's very difficult to disturb a property and maintain that original infiltration rate. And it would be wrong to say, gosh, it's a piece of cake to infiltrate. But it can help. Infiltration can help. But certainly the water going to the filter has to be clean. It has to be clean for two reasons. One, you don't want to hurt your infiltration rate. But number two, there is a finite life to every infiltration field. Anybody that's ever built septic tanks or used one can tell you there's a day when the field is going to fail. So infiltration is a useful byproduct. It's something we should try to do. We should be in a panic from day one to keep the water as clean as possible going to infiltration. I'd love to see it go through a pretreatment device, a cistern, and then run off a landscape slowly so that what actually gets to that filter and what we want to infiltrate has almost nothing in it, that it has really had an excellent chance to have even the smallest particles removed. Reducing the runoff obviously helps save stream banks, and it will help flooding and infrastructure issues from the big picture for jurisdictions. Jurisdictions that have flooding, jurisdictions that need to replace culverts that need to be bigger. Reducing that runoff volume is obviously going to help all of those problems over time. And using effective pretreatment not only makes reuse and infiltration practical, it makes maintenance easy and affordable. And remember, without maintenance, this kind of approach is absolutely doomed. Some people have said, hey, it's time for low-impact development. And you know what? It's going to be time for low-impact development. We've got to be careful how we implement it from a stormwater side. There's other things of low-impact development. I know it's not just a stormwater issue. But if we're going to address the stormwater issues, it can be done. And we are now getting to the place where we have the technology and the intelligence to apply these systems and make them sustainable over time. This is always my last slide. What my company is about and what the Stormwater Equipment Manufacturers Association companies are about is getting this material out of the stormwater so that all of it works better. The infiltration works better, the reuse works better, the protection of the channel banks works better. As long as we can get this material hopefully in a secure landfill or in a proper set of disposal. So, a wastewater treatment plant can be the right place to dispose of some of this material under the right circumstances. Maybe we'll see a whole lot more lakes and waters like this. So I appreciate you guys being here. I'm willing to take some questions from you. This is we like to think it's settled law, so to speak, but really this is emerging science. We don't have a whole lot of LID developments that have been out there 10 years, and 10 years isn't but a tick on the clock for sustainability. I'm proud to have some devices out for over 10 years now, but that's just getting started in stormwater.
Well, thank you, John. I know we had a small group today, but if anybody has any questions, you could type them in the lower left-hand corner of your screen there in the IM session. In addition, please, I made a couple of comments in there, but just in case you missed them, our 2011 webinar schedule is up and posted, and you can register for those events at www.cstwebinar.com. We've got a couple of special webinars that are going to happen this year. One of them being we'll have a guest speaker that will be announced here shortly. And lastly, we're working on putting together a panel board on stormwater where you can basically ask the experts and email your questions in or ask them during the session, and we can try to address them as in a timely manner. But other than that, if nobody has any questions, thank you for attending. You can, if you're looking for a certificate of completion, you can email me at jbenty@crystalstream.com. I previously posted it, but I'll put it up there again. And if you have questions specific to this presentation with John, you can feel free to email him. His email is johnmall@crystalstream.com. And once again, thank you everybody for attending. John, it don't look like we have a lot of questions, so I guess that'll about wrap it up. You held it right to an hour. Excellent. Thank you for your time, and look forward to. Hope everybody has a happy and safe holiday.